I'd like now to talk about Le Chatelier's principle, and it basically states that if a stress is placed on a reaction at equilibrium, the reaction will shift in the direction that will compensate for that stress. So what I'm going to do is I'm going to give you two examples, and what we're going to look at is the effect of adding adding a product in this case, and removing a reactant. So let's take a look at how we might do that. And here's what we've got. We've got our reaction here, 2SO2 plus O2 gives 2SO3. And what I'm pretending is that equilibrium looks like this. So we're going to have 4 SO2s, 4 O2s, and 6 SO3s. This is completely artificial on my part. It's completely arbitrary. I've just come up with this as being the equilibrium conditions. Now if we figure out what K is, since we're at equilibrium, we can do that. We can figure out K. It's going to be SO3 squared over SO2 squared times O2. And it's going to be 6 squared, which I've just gotten by saying there's 6 of these. 4 of these and 4 of these, so we're going to get 6 squared over 4 squared times 4, which comes out to 0.5625. So that's the value of K that we're going to get from that. Here's what I'm going to do. I'm going to add some SO3. So I'm going to keep the value of SO2 constant, the value of O2 constant, and I'm going to add in 3 SO3s. So if I do that, now I'm not going to be at equilibrium anymore, because by adding product, I'm actually changing the value of Q. Q is going to be different to K, so we're definitely not at equilibrium. And I'm going to come up with 1.266 as my value of Q. Now I do that just by substituting in 9 instead of 6 over here, so Q is going to be greater than K. So the question is, which way is the reaction going to shift? Well, the reaction is going to shift so that Q becomes closer to K. That is, Q has to become less. And Q can become less by decreasing the amount of products or increasing the amount of reactants. So what we would say is that by adding SO3, what's going to happen is that the reaction will end up shifting towards the reactants. And the reason it will do this is so that Q can be lowered in relation, so Q can be lowered so it can get to K. So let's look at the situation where we're removing O2. So we're removing a reactant here. So what I've done is I've still got 4 SO2s here, I've still got 6 SO3s, that's in relation to the equilibrium over here, and I've taken 2 O2s away, so we've removed 2 oxygens. Clearly we're not at equilibrium anymore because the value of Q is going to be different to K, it's going to come out to 1.125. And again what we're finding is this, is that by removing a reactant, the value of Q is now greater than the value of K, so the reaction will tend to move towards the reactant side, or away from the product side if you like, so that Q can be closer to K. Now both of these things make sense in the context of what we're doing, because if we're adding in product, the reaction is going to say to itself, well, what are we going to do about that? It's going to you want to use up the product and get rid of some of that product that we've added, so it will shift towards the reactant side to get rid of it. By the same token, removing a reactant, removing O2, the reaction is saying, well, how am I going to replace the O2 that was removed? Well, it can do that by going from the products more to the reactant side. So all of this still makes sense in terms of Q and K. Now, I would also like to point out that if we removed product, what would happen is the reaction would move to the product side, and it would do so in order to replace the product we removed. Likewise, if I added more reactant, added more O2 for example, the reaction will shift towards the product side to get rid of the O2 that I had added. And all of this would be brought out in the same kinds of calculations if we did those Q in relation to K things that we just did for removing O2 and adding SO3.